Welcome to the fourth paper session of this NordicSMC conference. The topic of this session is on sound analysis, and we have four papers looking at different aspects of sound analysis. If you have attended previous paper session in this NordicSMC conference, perhaps you're already familiar with the format. If not, what will happen right now is that we will watch at the four videos presenting the paper back to back, and at the end, we will have approximately 20 minutes for Q&A. If you have a question while watching the video, you can start writing them down in the Q&A window of this Zoom webinar. If not, we can start watching the video. The four papers in this session will be sound source localization using sector-based analysis with multiple receivers by Michael McCree, Leo McCormack, and Bill Blucki from Aalto. Then we have another paper from Joel Linford, also from Aalto. The title of his work is User Location-Based Loudspeaker Correction. The following paper would be Improving Interpretable General Recognition with Audio Feature Statistics Based on Zygotic Theory from Igor Batulkin from Technical University Dortmund. And the last paper would be Towards New Analysis and Visualization Software for Studying Performance Pattern in Hardanger Fiddle Music by Alexander Tiedemann, Olivier Lardillot, and Mats Johansson from University of Oslo. And I believe we can start with the videos.
Hi everyone, my name is Mike McRae. I'm going to talk to you today about sound source localization using sector-based analysis with multiple receivers. This work was done in collaboration with Leo McCormack and Veli Pulkki at Aalto University. This work belongs to the context of parametric sound scene synthesis, which has recent application such as 6 degree of freedom sound field navigation. But more specifically, this work is concerned with the sound field decomposition part of the problem, and more specifically, how to localize sound sources within a scene using multiple spherical harmonic receivers. One of the sound field quantities that we're going to need for this is the sound intensity. The sound intensity tells us important directional information about sound propagation in the sound field. So the intensity is composed of the pressure and the velocity, and we can recover the pressure from a single microphone, whereas to recover the velocity, we're going to need multiple microphones, which capture the pressure gradient. So a common way to capture spatial sound is with an ambisonics microphone, for example, which will give us such a signal. If we're working in the ambisonic domain, that makes sound field analysis particularly convenient because the first order components of an ambisonic signal correspond directly to the pressure and the velocity signals that we need to calculate the sound field intensity. In particular, it can give us the active intensity, which is going to tell us the direction of net energy propagation. And we can infer from that the direction of arrival of a sound source. So if we further normalize that active intensity metric by the energy density in the sound field, we get a sort of measure of how much energy is propagating from one direction versus all directions. And we call this the diffuseness. And this works fairly well for identifying a single sound source at first order, but first order analysis becomes insufficient as soon as you have more sound sources in the sound field. This is where the higher order signals become useful, because then we can apply spherical harmonic beamforming to just concentrate our analysis on one part of the sound field. So what we do is we essentially take 4 copies of our sound field, the original, and then 3 copies that have been spatially filtered to have the directional sensitivity of dipoles. And then that gives us the 4 components that we need for the sound intensity. But further, we're going to apply this spherical harmonic beamformer, which we call a sector, to each of those copies of the sound field to then focus our estimation of the sound intensity just within that region defined by the sector pattern. So let's see what this looks like in practice. So consider a sound field that is composed of just purely noise in all directions and a single sound source. So we see the results of analysis at first order here in the top row, where these directional vectors are DOA estimates. The short estimates indicate high diffuseness, and we see that in a purely diffuse field with no source energy present, they point in all directions. And then as the source energy is increased, these DOA vectors begin to gather towards the source and increase in length. Now, if we use sectors to process that same sound field, with a pure noise field, we can see that already the sector is providing directional emphasis in the direction that the sector is pointing, which in this case happens to coincide with our sound source. And then again, as the sound source increases in energy, then we converge on a perfect estimate when there's no noise whatsoever. We get even better results at this fourth order analysis, and we can see that as long as the source coincides with the direction of the sector, we get very good estimates. But if the source moves off axis, then something interesting starts to happen. We can see at first order, the analysis, the DOA vectors will just track that source, but at this sort of sporadic, consistently poor estimation accuracy. Whereas if we use sector processing, again, we have a great estimate when the source is on axis, but as that source moves off axis from the sector, we sort of lose sight of it and become totally blind to it at some point, and then the sector only sees the diffuse field. And so what that means is, as long as our source angle of arrival is low, then we have very high accuracy with sector processing. But then as that source moves off axis, we get higher and higher error to the point of being worse even than at first order analysis. Now, if we sort of combine those two cases, for this instance where we have two sound sources, where one we consider a target that we want to localize, and the second being an interferer, we can see here that at first order, as that interfering source moves off axis, it's going to draw the estimation away from the target source because essentially we have no spatial discrimination, and we're seeing a spatial average of the energy between those two sources. But as the sector order increases, we increasingly reject the energy of the interferer as it moves off axis. So we see that the farther off axis our interferer is, the better our estimation becomes, especially at high orders. So now that we know a little bit about how this performs for DOA estimation, we can extend this to 3D source localization. And we're going to do that by extending our DOA estimation vectors into space from the direction of multiple receivers. And then we're essentially going to estimate the source position as that which is the least distance to all of those projected DOA vectors. So here we have two receiver arrangements, and in this case, the sectors are pointing towards a focal position indicated by the triangle, and we have a source that moves from that focal position into outer regions of the space of interest. So we can see in this first source position that coincides with the focal position, we have very low error, and then as that source moves away from the focal position, it increases. But then an interesting thing happens here with the two receiver arrangement when the source moves directly in between the receivers, and that is the DOA vectors are essentially becoming collinear, so slight variations in their estimates are going to cause very large translations of the position estimate, creating these peaks of error in rather unpredictable areas depending on what the order of analysis is. But then if we add a third receiver, we lower the error quite a bit, and the error becomes consistent across different receiver arrangements. So if we extend that analysis then across space, we can see the effect of both adding receivers from left to right, as well as increasing the order from top to bottom. So we see quite high error here in the first order case with just two receivers, but then as we add receivers into the space, this area of low error increases. As we increase the order of the sector analysis, then the error minimum continues to lower, and the region of accuracy grows. So we can see by the time we're at fifth order analysis here, we have very low error over a wide region. We can improve our estimation by anticipating that certain receivers are going to be able to perform better than others. So we can modify our localization algorithm to accept weights for each of the receiver DOA projection lines, which will essentially draw our source estimate towards the receivers that we have higher confidence in, or towards their projection lines, that is. So one such way to do this would be through distance weighting, in which case we have an initial source estimate, and then based on that initial source estimate, we would apply a higher weight to the receivers which are nearest to the source. And we expect that that source will then dominate the energy of that receiver, giving us a higher accuracy in its estimate. So in this case, when we applied such a weighting, we increased the minimum error area from about 2.5 square meters to about 4 square meters. Now, to conclude, we can see that the sector-based approach to source localization is shown to be a pretty consistent improvement over the traditional first-order method. This operates primarily through mediating the direct to the diffuse energy, which is essentially a spatial signal-to-noise energy ratio. However, we do get diminishing returns if our target source veers too far off axis from our sector heading. We see also that there are possibilities to refine our estimates based on observed, inferred, or a priori seen conditions, and that the best localization consistently anchors around the focal point of the sectors with a slight bias towards the centroid of the receiver arrangement. And then finally, complexity emerges quickly. So in order for robust localization, there are a number of considerations that have to be balanced. So that's it. Thanks for watching, and I look forward to your questions in the Q&A.
Hi, I'm Joel Lindfors, and this is my presentation on user position-based loudspeaker correction. So, let's start with the basics. Rooms create a multitude of issues in audio reproduction that loudspeaker correction aims to help with. These include modes and reflections that create perturbances in the frequency response of the audio system. However, the issue is that the modes and the reflections change with the position of the user. So the conventional loudspeaker correction can't account for all of the movement of the user and the different listening positions that the user takes. On top of this, loudspeakers themselves are directed. So listening to a speaker at 30 degrees will sound different to listening to the loudspeaker at 0 degrees. The solution is to change the calibration based on the receiver's position. So we create an inverse filter based on all measurements. We EQ any outgoing audio with the inverse filter corresponding to the listener's position. And this is what we call user position-based loudspeaker correction, or UC for short. And how exactly we do this is a program tracks the center of an Aruco marker, which is this black and white marker you see on the right. And when the program confirms that the position of the receiver is correct, we play a test tone. So basically the program tells the engineer to move the microphone within the red square you can see on the upper right picture. And when the engineer knows that it's in the right place, he places the marker on the microphone and the program confirms that the microphone is in the right place. After that, we play the exponential sine sweep to get the frequency response of the loudspeaker system in that exact position. So we track the receiver using this Intel D415 depth sensing camera. So we're tracking in 3D. We have a video feed and a depth feed. And the program tracks the measurement process and the playback. And on the backend, we use open source object tracking algorithms from libraries such as dlib and OpenCV. For the EQ, well, historically, analog graphical EQs were used for room correction. However, recently DSP has been gaining in popularity, and we used a digital graphical equalizer designed by Dr. Juholiski. The reasons for this was the low latency and the high computational efficiency and the low error in the response of this equalizer. So we started development for a real-time implementation, but due to the time constraints, we did not reach a good enough version to test on human subjects. We have the proof of concept, and it works all right. However, future research should delve into this more. We did, however, do objective measurements, and that's what we're going to look at next. So what exactly did we measure? We measured the UC's performance against different types of correction. We measured it against non-corrected speakers with static correction, which would correspond to a conventional loudspeaker correction. And we also did a nearest neighbor correction, which is basically UC but with a lower mesh resolution, and an interpolated correction, where we interpolated the gains of the EQ bands from the UC measurements to see if we can artificially increase the mesh resolution of the UC and still perform as well. We did all of this in a cuboid structure that you can see here. So here, each red dot corresponds to a measurement point. In the center of this cube is what we call the listening position, and it's also the static correction position. The blue dot there is the interpolated measurement position, and we had a total of eight of them. And all of the red dots here are a 5 centimeter distance from each other. So we measured the system in my studio room in Espoo, and all of the measurements suggest that the UC improves the loudspeaker's frequency response more than conventional method does. And here are some results from the measurements. So here we can see a single point room response before and after correction. On the red, we can see the frequency response of the loudspeakers with no correction. And on the green, we can see the frequency response with UC applied. On black and with the red dots, we can see the EQ gains and the expected EQ frequency response. Next up, we have the UC versus static or conventional correction in the studio room. On blue, we have the static correction, which you can see is performing quite well, but still it's being outperformed by the UC in green. And finally, we have the averages of the decibel ranges for each method. Smaller value means better. The range basically means the difference between the highest and the lowest decibel value of the frequency response. So what we did here was we took all of the measurements for each method and we averaged the ranges for each of the methods. And here we can see the UC is outperforming all of the other methods, including no correction in red, SC, static correction in blue, NNC in green, and LIC in yellow. LIC standing for linear interpolation correction. So, in conclusion, a novel loudspeaker calibration technique was measured and pitted against other methods: no correction, static correction, nearest neighbor, and interpolation correction. The suggested method outperformed all other methods, and future research should delve into the real-time implementation and subjective evaluation, and it should also delve more into interpolation and upscaling the resolution of the mesh, because the measurement process is quite laborious, and interpolation shows promise in outperforming static correction as well. Here are the references, and thank you.
Hello and welcome to my presentation, in which I'll show you how audio feature statistics based on Zygonic theory can be used to improve interpretable music genre recognition. Zygonic theory was presented by Adam Ockelford, and its task is to search for relationships or similarities between changes in series of musical events. Let us start with an example by Ludwig van Beethoven. Here, with regard to mode duration, we have 8 notes followed by quarter notes, and here it is the same. That means that the change is the same. We have a perfect match, a perfect zygon with respect to mode duration. With respect to pitch, if we look at this upper movement, so we have one half tone down, one half tone up, two up, and here we have two down, two up, and two up. So it means that this match is almost perfect, an almost perfect zygon. So if we want to apply music genre recognition, very often we do not have the score, we have audio signal. From the audio signal, we can extract features like frequency capstone coefficients, spectral characteristics, pitch class profiles, and so on. Well, we have typically numerical some continuous values, and then first of all we run discretization, so we have that values, so we can also apply search for n-grams. And here you can see the change is +2 + 1, +2 + 1, so it's the same. We have a perfect zygon of length 2 based on the original sequence of length 3. We can also search for inverse zygons like here, so it's +2 + 4, -2 -3, so it's an almost perfect inverse zygon. And we can also search for zygons for features with more dimensions than 1. For example, here we have 2 dimensions, and we can estimate the changes for each dimension individually. To extract zygons from audio signal, several steps are required. So first of all, one or several base features should be selected. Then the original feature values, which can be extracted for very short frames, are aggregated for longer time frames with a duration closer to a typical note duration. Then the values are discretized, and finally derivation is computed. So this table presents parameters and settings used in my study. As base features, I use 39 sets presented in the next slide. Aggregation window length is between 250 milliseconds up to 3000 milliseconds, depending on feature. 2 discretization methods I used, first using quartiles and then histograms with 10 bins. Then for statistics based on zygon occurrences, I used 2 analysis window lengths, one with 30-second length and 15-second step size, and another one with variable lengths estimated by music segmentation. All dimensions of feature set contribute to the zygons, so I use only multi-feature zygons. The lengths are 2 and 3. That means that the original sequences of discrete values are 3 and 4. 2 zygon types are used, direct and inverse, and 5 different perfection grades are defined from perfect zygons to imperfect zygons. The base audio features should represent different meaningful musical properties and were carefully selected after some preliminary experiments. So the details are provided in the paper. Just a brief overview. So I have 3 different energy feature sets, then a larger number of different harmonic descriptors with many low-level features, but also some specific features like chord vector, tonal centroid, and so on. And then I have some features derived after own previous work. So the first one is based on approximations of unknown audio signals using evolutionary algorithms, so where original samples of individual instrument tones are combined, trying to approximate instruments and also pitches. And then I use instrument predictions based on convolutional neural networks applied also to combinations of different samples. Then 3 groups of rhythm and tempo features I used, and finally several different descriptors of timbre. The experiments are designed in the following way. So the task is to recognize 6 genres and 8 styles using binary supervised classification methods. Each time the training set is defined by 10 positive and 10 negative tracks. So this situation should be close to a real-world scenario where a user would prefer to select only several music pieces to define some category. And then I use optimization sets to evaluate feature selection, and after the optimization again, their results are evaluated on the test set, which is artist and album independent. So it means that the test set does not contain the same artists and albums as used in training and optimization sets. 4 different classification methods are used, and evolutionary multi-objective feature selection is applied with 2 goals. The first, to minimize balanced classification error, it's performance measure, and then also to minimize the number of selected features. So we try to also to learn interpretable characteristics, the most relevant, the most important features which should be helpful to predict a genre. Statistics based on the goals contributed overall to more than 3,000 different dimensions. So first of all, we have this longer analysis frames. I measure the numbers of different zygones estimated there, and also numbers of all sequences contributed to zygon estimation. That means, for example, if we have some energy characteristics as base features, a high number of zygones in a segment or in a longer analysis frame means that we have very often close relationships between some sequences. The baseline from the previous work uses 566 different semantic descriptors. Here this table presents an overview. There are chroma and harmony descriptors, chord statistics, several predictions using supervised classification models like instruments, moods, and various descriptors designed in a particular study by musicologists like female or male vocals, melodic range, and so on. And then we have temporism and structural complexity statistics. That means it's a rather large set of meaningful, interpretable characteristics which were quite successful to predict musical genres and styles. For now are the results. The goal is to minimize the balanced classification error. So it means the smaller numbers are better. Here we have all genres or styles, and here we have different sets of features. So this is a baseline using semantic features, and then feature selection, then zygones using quartile discretization, using histogram discretization, and here are the results when we use both zygones and semantic features, and again zygones with semantic features. So bold values mean here that feature set with zygones was better than semantic feature set, and underlined numbers are the smallest errors for each category. So here we can see that only for 2 of categories semantic features were better without zygones. We can also see that if we use only zygones, we have not so many bold values here. That means that they're typically not so good as semantic features, because the semantic features from the previous work, they were actually quite powerful. They describe many statistics, but not so that there's similarities and relationships. But if we start with the combined sets, we can see that in many cases we can achieve smaller errors. So it means that statistics based on zygonic theory can indeed contribute to better recognition of music genres. Coming to conclusions, in my work I have presented interpretable audio features based on zygonic theory. 39 different base features were used to characterize relationships in different meaningful music properties. And we can see that when we extend the original baseline feature set with semantic descriptors using zygonic statistics, the error is reduced for 12 or 14 categories. Because the zygon extraction and also the extraction of statistics based on zygones has a large number of different parameters, future work should include further parameter tuning, but maybe also the search of specific zygones, and of course usage of larger data sets. Thank you for your attention.
Hello, my name is Alexander Tiedemann, and welcome to my presentation on some new visualization and analysis software for studying performance patterns in Hardanger fiddle music. Now, this study was the result of my master's thesis at the MCT program here at the University of Oslo. Now, the Hardanger fiddle is a vital component of Scandinavian and folk music heritage, dating back to the late 17th and early 18th century. And with such a long-standing tradition, the unique performance patterns of Hardanger fiddle music have interested folk music researchers and musicologists for some time. Today, researching performance patterns is an increasingly complex task that requires interdisciplinary research approaches, often bringing together musicology, computer science, psychology, library science, anthropology, and much more. Now, there is very little computational research on Hardanger fiddle performances, and as a result, software frameworks that consider contemporary research perspectives on Hardanger fiddle music are quite scarce. However, the Mirage research project is currently contributing to this scientific body, developing advanced MIR frameworks that build on recent musicological research. Now, this paper, in collaboration with Mirage, examines how we can design better and more user-friendly computational tools to reveal performance patterns in Hardanger fiddle music. Now, to try to reduce the scope of my study, I decided to only consider specific rhythmic traits of springar performances, a particular subgenre or style of Scandinavian folk music. Now, most springar styles are rhythmically structured in triple meter, so 3/4, just as waltz is. And they are often accompanied by solo Hardanger fiddle performances. Now, some regional variants of springar possess the interesting stylistic feature of asymmetrical timing patterns, which refers to the systematic unevenness or asymmetry in the duration and position of the musical beats. And recent studies have shown that beat level variations to this asymmetrical timing patterns of springar performances seem to be related to melodic rhythmic structures, in a sense, meaning that particular motivic segments are often associated with particular timing profiles, suggesting that structural and other expressive features influence beat duration patterns. Now, inspired by this novel research, my study presents the development and evaluation of 2 software prototypes that enable structural and multidimensional perspectives on the complex rhythmical structuring of Hardanger fiddle springar performances. And the goal was that the evaluation of these tools would generate an evidence-based discussion that would ultimately address the research question and constitute grounds for some more research. The evaluation procedure featured a series of operational tests and also a questionnaire directly following an online presentation. The operational tests, they measured whether the prototypes produced data that was consistent with contemporary performance studies and symbolic representations of the music, so the musical notation, basically. On the other hand, the questionnaire was designed to collect systematic feedback on more aesthetic and conceptual aspects of the tools. Now, the findings were quite interesting, and just to name a few, there seems to be a demand for these types of computational research tools in Scandinavian folk music research and in musicology in general. And it was also evident that the tools that I prototyped had the capabilities to accommodate for at least some of these demands. There was also a clear preference for tools that are able to reveal relationships between musical dimensions, and then especially the link between musical practices and performance parameters. So, for instance, being able to explore how bowing patterns are related to melodic structuring, or how the foot stomping affects rhythm, etc. And finally, in order to tailor to an audience that has varying degrees of musical and technical knowledge, these tools should ideally include features that can help guide the interpretation process. So make it easier for people to make sense of the data or information that is generated, which also effectively reduces the chances of misinterpretation of the data that they generate. However, there are some methodological limitations that directly affect how the results of my study should be interpreted and understood. For instance, there are only 4 subjects that completed the questionnaire, which means that none of the survey results can actually be considered statistically significant. Also, the operational tests are limited in their scope, and the findings are based on a rather small sample size. So instead, I propose that these findings should be interpreted more as valuable feedback and guidance toward further development and a more refined study of this matter. And speaking of further development, in my article, I propose a few improvements going forward. So number 1, future development should see a software migration from NordicSMC to a web application. A web application is more maintainable and has better support for interactive and UI design elements, and they facilitate a more complex and varied functionality. But most importantly, a web solution would actually render the application to be more compatible with other software and frameworks. And this is number 2 on the list. So considering that the body of work that has been done developing advanced analysis frameworks, for instance at Mirage, I think it would be wise to adopt a more dynamic approach to developing these kinds of research tools, in the sense that it should be much easier, or should be very easy to integrate them with existing frameworks. Third, a more systematic and longer evaluation procedure should, of course, be considered. And having more carefully designed features in a web-based solution could also enable a better evaluation procedure, in that it could enable you to collect much more data and also to reach more people in a shorter period of time. Okay, so that's the end of this introduction. I really hope it was interesting for you. And if you have any questions at all, do not hesitate to ask. Thanks.
Okay, thank you very much. Thanks to all presenters. I think it would be great if you can come on screen. Perhaps here I can put Alexander on screen as well. Yeah, go to auto. Okay, so there were a couple of questions, I think 3 questions on the chat window. I think 2 have been answered. There's a question from Byron. I think that was for you, Michael, probably. I don't know if you want to try to answer. I think it was written shortly after the end of your video.
Okay, yeah, I'd sent him a message to try to clarify. But so the method that I introduced involves essentially spherical microphone arrays that are distributed around a room that are used to kind of triangulate sound sources. So it seemed that the question was more about like a psychoacoustic sound source localization from a perceptual standpoint, which is a different thing. So this is analyzing a sound scene to locate sources in space, irrespective of any sort of reproduction for sort of localization by a listener.
Mm-hmm. I have a question for you, unless someone else from the audience have a question. In your study, you presented result using 2, 3, and 4 receivers, and also first order, third order, and fifth order. I'm wondering if you can say something about how the computational complexity scale up with the order and with the number of receivers.
Yeah, that's a good question. So it's using spherical harmonic processing, and the number of channels for each order will scale. It's the order plus 1 squared. So if you have a higher order signal, say 5th order, then you have, 36 channels of audio. But if you know that your scene is fairly simple, if you have 1 or 2 sources, and you know that it's quiet, there's not a lot of interfering sound, then you don't have to use all of those channels. So the nice thing about ambisonics is that it's hierarchical in the sense that you can use lower order even if you have higher order available, and so you can throttle your system in a sense if you're trying to get it to run in real time and you're running into issues.
Okay, and Another question would be more on the application. I mean, when you introduce your work, you mentioned sounds in synthesis, and in your results you presented, I think the average error, some sort of like ranging between, I don't remember, it was like 2 to 5 meters, something like that. I'm wondering what would be a good threshold, in terms of like what would be an excellent and what would be an acceptable threshold for the error, and perhaps this threshold may be different in different type of applications.
Right. Yeah. So the scenes that I was analyzing, so it's simulations of about a 35 square meter space. So you could imagine, I sort of tried to gear it around like perhaps a conversational distance between people. So in that case, if you're trying to segregate between neighboring sound sources who are interacting, if they're people, then you would want some sort of accuracy, I don't know, within a meter or two, right? But if this is an outdoor environment or something and you have sound sources that are moving, it really depends on the sort of dynamics of the sound scene. And so if for example, you are, let's say you're in a large room and you know that all of the activity is happening in one direction, you can focus all of your analysis and your sectors and everything in that direction to sort of increase the spatial resolution in one direction. Whereas if you want to analyze an entire scene, then you're going to need to use more of these sectors to discriminate space. And I guess to connect it back to your original question, more sectors means more concurrent analysis, and so higher computational complexity. Yeah, I'm not sure exactly how to answer the question about a specific threshold. I guess that's something that you would need to decide as the user of the system what's acceptable, and then scale the order of processing accordingly.
Could I have a follow-up question there in terms of the scalability, or perhaps moving this between, thinking about different spaces? Could you learn something from one environment when you kind of set it up in a different, in terms of being able to reuse some of the knowledge about the different sectors, etc.?
Do you mean if you tune the system for one environment, how well does it translate to another?
Yeah.
That's a good question. So this would be just speculation about that, but the time scale of analysis is, it's very short. And so if you wanted to identify even like room reflections and things like that, you could have that time scale resolution. But a lot of the results that I presented were, statistical averages. And so if you were doing this with real sound sources that are active in a space, you're going to need to, very finely tune what sort of averaging windows you're using and whatnot. And so if you're in a fairly anechoic environment, like open free space, then you don't have to worry as much about sound reflections and that sort of thing. Whereas if it's a highly reverberant environment, you're going to need to really drill down and sort of tune the system to try to reject those reflections. Yeah, I guess the answer to a lot of this is it depends on the complexity of the sound scene.
Okay, thank you, Michael. And I think we can now move to the second work. We can speak with Joel. There was already one question that you answered, but there is a follow-up comment from Vesa, and I believe that he asked you to comment a little bit on the update rate, how many times per second the equalizer should be updated, and if you tried yet different update rates, and how did it go?
Oh yeah, well, that was the part where I ran out of space for my text answer. Was the update rate? I think the update rate it depends on the mesh resolution, i.e., how far the original measurements are from each other, and the how much the user moves their head. So if the user is very still, then you don't have to update the EQ at all. But if the user moves a lot, then you will need to update it a lot. In the testing of my because I did the real-time implementation that I didn't do any studies of, but I did the implementation and I tested it, and like with my subpar programming skills, I was able to get it to work where basically there was no limit to, well, the buffer is always the limit to the updates, but there, like beyond that, there was no real limit to how often we could update the EQ.
And just by looking at your the illustration of that mesh, is it correct? Am I correct if I say that the spacing between the points was approximately 5 cm, right?
Yes, that's, yeah.
So
exactly.
So it's a 5 by 5, so it's a 25 by 25 by 25, right?
Yes.
And I mean, if you want to cover a larger area, can you still work with a 5 by 5 by 5, so a total of 125 measurements? So perhaps you can actually increase the distance perhaps from 5 to 10, or you need to stick to 5 cm, and therefore you need a much larger number of measurements if you want to be able, perhaps you're in a larger studio and you'll be moving a little bit more than 25 cm.
Yeah, well, the reason I for this presentation I went with 5 by 5 by 5 times 5 centimeters was because that's like sort of the maximum area that I usually move in when I work in a studio. But if I wanted to increase the distance between the measurement points, there's no reason why that wouldn't work. Obviously, you will get more error at the very edge of a certain measurement point, as one would expect. But that's about it. There's no limit to how much to how large of an area you can cover. Then of course, if you want to, because the 5 by 5 by 5 was sort of the upper limit of how many points we could measure without running out of time in a day, because 125 sine sweeps takes about, well, the measurements took about 1 to 2 hours per scene. So if I want to have a larger mesh, that's not feasible. But if we have a larger distance between the two measurement points, then we might be able to use interpolation to cover the points in between. That was sort of the reasoning behind why I went with the interpolation measurements as well.
Thank you. And if my understanding was correct, you're tracking using video also the position of the measurement mic, right?
Yeah.
So perhaps, I mean, it's also possible to, even if it's not ideal, to move away from that uniform mesh and perhaps have less uniformly spaced measurement points, because I believe that for, I don't know, for an average user it will be pretty difficult to stick to that grid.
Yeah, I mean, yeah, that's true. I would expect that the average movement in a space when you're listening to music is not rectangular. So a lot of the points are like not really relevant to a real situation. So you're right. Maybe like a circular mesh would be better, or one that doesn't have too much height movement, because there's like horizontal and vertical movement happen a lot more than up to down movement, or how should I say depth and horizontal movement happen much more than horizontal movement. Vertical movement. So yeah, there's no reason why we couldn't use a non-uniform mesh or a circular uniform mesh, or pretty much whatever.
Okay, thank you very much for your answer. And Igor, I don't know if there is any other question. I don't see anything here on the Q&A. Feel free to type something on the Q&A, or you want to ask something, Alexander?
Thank you, Igor. I'm really looking forward to read your paper in more detail, but could you I think I missed a little bit on kind of the beginning there of the feature extraction part and how you kind of the beginning of the pipeline of your system and the scalability there. Could you explain that a little bit more?
Do you mean Zygonic features or the baseline with other features or everything?
Well, the audio. Well, from audio to start with.
Okay, so it's basically I extract all features from audio. So it's converged to mono 20,000 hertz. And there are very different possibilities to extract some features with regard to different semantic properties. For instance, we have some harmonic features like pitch glass profiles, or we have some timbral features like Merrill frequency capstone coefficients. And the idea was to investigate these different feature sources and to try to search for some similarities, so some relationships between parts of features. So it's a very clear example at the beginning with the nodes. So you can see that if some features, for example, if they move up and down and the same movement appears sometime later, then Ockelfold calls this Zygon. So it means it's not the features themselves, but their change is taken into account. And if this change is exactly the same, we have a perfect Zygon. And if this change is slightly different, then we have almost perfect Zygons, and we can define this perfection grade. And the idea was to, so if we typically if we classify genres, we don't have the score. So from the score, we can get very important information on instruments, on harmonics, that's everything there, but from audio, it's not available. And my idea was to try out, so these relationships, they can be extracted from audio features. And the question was, can they help to improve also the genre recognition?
Sure. No, I got that part, but I was just wondering, did you think also about how this relates to perceptual features, or has that been part of your thinking as well?
Maybe not directly.
No.
It's rather from maybe from musical properties, like for Zygons, it's for the difference between pitch or note duration, or the difference between rhythm and tempo can be also taken into account. And that different semantic musical properties, they can be identified from audio features, or audio features can be grouped with regard to these properties. For example, one group is describing the instrumentation, like which instruments are playing there, and also are the changes of some instrument predictions the same or very close on one time point and another time point, and how often does it occur?
Okay, cool. No, but I'll read the paper in more detail and get back to you with some more detailed questions.
Yes, sure.
Yeah, I have a comment and actually a question still on the phase in which you extract the features. And I mean, since the starting points are the Zygons, that are usually defined, they're usually computed over the score, the symbolic representation of music where the time is quantized. When you analyze when you compute the low-level features from the audio signal, do you use the same analysis frame or analysis window for all the different sources, or perhaps you use an analysis frame and analysis window that is tempo related, so you quantize it based on the tempo of the specific song?
Yeah, I have tried different methods. Although the problem, not tempo, rather onset. So I have applied also some onset detection and also bit detection. And then I try to use features, let's say, only around onset events or only from some time frames. The problem is that the tools which extract onsets only based on audio, they do not perform really well. So there was no real statistical difference between the method which simply aggregates some feature values, let's say for 100 milliseconds, and then this bitwise or onset-wise aggregation. And then, so if I use the smaller time frames, then I can discretize the values. I map them to some to n-grams or some numbers which are discrete, like 1, 2, 3, 4, and so on. For the pen and for quartiles, I have 4 different possibilities, and for histograms, I had 10. And some preliminary experiments, I have also used 8 different quantiles, but it didn't perform better.
Thank you. And we have another question for you. Would be great if you can keep the answer short because we're running out of time.
Yeah.
From Olivier, how do you discretize the time series into successive symbols so that you could define the time points for the distance between successive symbols? Hope I'm clear.
So the discretization can be done in 2 ways. From the time point, I just simply use the frames of a constant length or this bitwise aggregation. And from the vertical component, so I just put all feature values from the music piece into one vector, and then estimate quartiles or quantiles. So it means I have statistics, and then I put this to these bins. So for example, to features, the feature which has a rather low level, also a rather low value, it's mapped to 1. And the feature with higher value, between the first quantile and the median, it's put to 2, 3, and 4, and so on. So I hope it's understandable.
Okay, thank you, Igor. And questions for Alexander. I will ask a couple of questions since I have to pass you the microphone. So the first one is, I mean, the starting point for your work was analysis of Hardanger fiddle music, but I'm wondering if that tool, or perhaps the tool with minor variation, can also be useful for analyzing other type of music. This is the first question. And the second question is, to what extent in the tool it's possible to automate or semi-automate the process of doing those adjustments, because in one of the windows, actually, the user has to adjust those like vertical lines, and if this can be somehow automated or semi-automated, if it makes sense at all.
Interesting. The first question about using the tools for other types of music is absolutely fine. I mean, it's based on output of systems that Olivier and Mats work on, or Olivier at Mirage. So they're basically just importing data into the systems, and they generate these systems. So if you import more data in there, you can have a better analysis, basically. So the tools are in their essence, they are more like data visualization management tools, right? Because you can take in loads of data and get some very nice visualizations and very nice ideas of certain traits about the music, certain relationships, and then you can export in other types of formats or whatever. So I don't know if I said that in the end at the future research part, that it would be interesting to use these tools in conjunction with like machine learning and stuff, like creating actual data sets was the thing. And your second question about adjustments, actually an interesting thing was that at the very end of the project, I started to develop a thing where you can actually edit structurally those beats. Because as you see in the window, you're actually editing the beats of the music. And one interesting feature that I did develop, as I said, but was too late in the project, was the ability to make the adjustments that you make propagate sort of throughout the structures of the music. So you can actually edit the second beat of a motif, and the second beat of that motif throughout the whole song would change accordingly, in a sense like that. So those were things that we sort of theorized about and tested out, but they're absolutely worth working on further, like for future testing and more research. Yeah.
Okay, I think there is another question from Valent. In your demo, you showed selecting phrases and performing a lookup of similar occurrences. How is this similarity calculated? KD3 or something similar? Have you thought about clustering these motifs and perhaps visualizing them in some way? We have a minute left.
Clustering, there were many ideas about the visualization of these sort of motifs and clusterings, but there were just so little time to actually get there. The lookup is actually based on, it's like a recursive loop of looking for similar, similar properties within a certain scaling range. So you can scale, and then you can search for similarities throughout the music, and then you can sort of increase the scale or reduce the threshold for searching, basically. So it's a very basic sort of pattern finding system. And when this sort of system worked, I thought about how much better and more elegant it was to just integrate the existing features, you know, in what sort of frameworks would be best for doing that kind of development, in a sense. So you don't have to sort of create the wheel again, in a sense. But it was a nice thing to just demonstrate the conceptual thing, but it wasn't a very sort of elaborate feature, if that makes sense.
Yeah. I think this was the final and last throw of the microphone. Thank you, Alexander. Thank you, Joel. Thank you, Igor. And thank you, Michael, for your work and your presentation. Now we'll have for a 10 minutes break before coming back at 11:20 for the final paper session on sound synthesis.